Assalamualaikum and greetings, dear our lecturer, Dr. Zahir and fellow friends. We are the members of Group 3 from 3 Bmka S1/2 and we are going to present our lab report for the design and analysis of car disc brake system. Allow me to introduce our group members. Firstly, Muhammad NORHAIZAD bin RUKIMAN, Muhammad HAIQAL bin HAMID, Muhammad KHAIRUDDIN bin ZAHARUDDIN, Muhammad YUSOFF bin Ali, and me myself, HASSANAH binti KHAIRUNSAM. Firstly, the main objectives of this lab session are to create a virtual reality model of a disc brake using 3D modeling software. Particularly, we use CATIA V5 and to determine the disc brake rotor's structural integrity and safety factor by specifying its material properties and analyzing its response to braking forces. To simplify the theory of a disc brake system uses a metal rotor and flat brake pads to create friction for braking. Hydraulic pressure pushes the pads against the rotor to slow down the wheel, and if one side's brake pad were unevenly replaced or refinish both front and rear brake discs together. Never replace pads on just one wheel. Also, brake dust can be harmful, so don't blow it away with compressed air, and wear a filtering mask when working on brakes for safety. In our lab session on design and analysis of car disc brake system, we focus on the safety factor. This factor is important to make sure our brake system works well and keeps people safe. It adds extra protection to account for unexpected situations and variations in material and load. Our goal is to enhance performance and guarantee safety and reliability in real-world situations by understanding and using the safety factor in our work. Next, we proceed with the procedure from how we sketch in 2D and turn the disc brake rotor into a 3D modeling.
This step collectively result in a well-defined brake rotor design meeting the specified dimension and including various features for attachment and braking functionality.
Brake disc rotor analysis is crucial for establishing key material properties such as young modulus, Poisson ratio, density, thermal expansion, yield strength, and core precision. This data is essential for assessing the rotor's ability to endure the stresses and temperatures experienced during braking, involving various testing and measurement methods to gather material characteristic and behavior information. Now we are going to explain how the analysis this brake rotor to do it. First, we apply the material is iron and then we study the drawing. Next, the center of the brake is clamped. The surface slider is added to the nut hole area and rear rotor. The area of brake pad is applied a distributed force and the load is set around 2680 Newton in z-axis, so does the rear rotor negative 2680 Newton. Then we insert the rotation force to the edge of rotor. After all the mentioned above are applied, then we compute the data. Before we go to the insert, one by one we check the deformation, von Mises and principal stress. Then we click the frequency case, then the static case solution at the collar area of brake pad is selected. The data once again is computed to obtain the data of deformation, von Mises and principal stress happen on the material. The data mentioned in step 7 is checked one by one to see the rotation of the brake rotor. The data obtained are generated to get the readings of yield strength, young modulus, and others to be explained in discussion.
Continue our presentation by explaining the data or our finding during the experiment. Material properties for rotative brake. So after the analysis, we generate the report. From the analysis, we can have the properties of material that we use for the rotatives. So the first one is on the list. The value is 211 exponent 11 Newton per meter square. Portion ratio is around 0.291. The density of our product is 7870 kg per meter cube. So the thermal expansion involved is around 1.211 exponent 5 Kelvin degree. So the yield strength is around 3.1 exponent 8 Newton per meter square. So as shown here, the material name is iron for our rotative. So next, experiment result. So here we can have the structure analysis result from the experiment. So we can have maximum translational displacement is only reached until 275 mm. So in terms of von Mises stress, we can have the maximum von Mises stress that is 3.14 Newton per millimeter square. So next, here the result for the maximum von Mises stress, that is, as I said before, 3.14 exponent 11 Newton per millimeter square. So the minimum von Mises stress is starting from 1.09 exponent 8 Newton per millimeter square. So the maximum translational displacement, it can only reach 275 mm. So we continue for the calculation part, which is involved in to define the factor of the safety. So FOS equal to the ultimate stress divided by the allowable stress. So in the experiment, we can assume the ultimate stress as the yield stress divided by the maximum Mises von stress. So 3.1 exponent 8 Newton over millimeter square divided by 3.14 exponent 11 Newton per millimeter square. So we can have FOS equal to 0.04915. So 0.0495 is actually less than 1, which is safe to be used as a material in creating a rotor disc. So I will continue the presentation by explaining discussion or our finding in the experiment. The importance of having a factor of safety in the product is to reduce the risk of failure. So in this case, rotor disc in a braking system always subjected to an interforce included and heat during the operation. A higher FOS provides a buffer against unexpected variation in load, temperature, or other operational conditions, and this will reduce the likelihood of rotor failure, which could lead a loss of braking effectiveness. So the second one is about the assure the structural design. So rotor disc, as we know, the structural integrity is essential for the consistent and reliable performance of the braking system. By applying an FOS, we can ensure that this can withstand the stress and the heat generated during the braking process without experiencing deformation or failure. So the last one is increase the safety of individuals. Okay, in this context of a vehicle braking system, a higher FOS ensure that the rotor disc can effectively and reliably dissipate the kinetic energy of the vehicle, and it will bring it to a safe stop. So this is paramount for the safety of passengers, driver, and pedestrians. So I will continue the presentation by explaining the discussion from the experiment. The analysis conducted in CATIA software revealed that voltmeter stress ranging from 1.09 exponential 8 Newton millimeter square to 3.14 exponent 11 Newton over millimeter square. By calculating the FOS factor of the safety as the yield stress divided by the maximum voltmeter stress, the obtained FOS of 0.04915 indicates that the component is considered safe for use under the given condition, as it is less than 1.
From these two slight abstract conclusion we made, we also can conclude a short main point passage to point out the main conclusion from this lab session. Is the lab report underscores the crucial roles of the car disc brake system in vehicle performance and safety. It highlights that material selection, design criteria, and maintenance practice significantly impact the system performance, particularly in terms of heat dissipation and brake effectiveness. Ultimately, the report emphasized the importance of a balanced approach to designs, materials, and heat management for creating efficient and safe automotive disc braking system, with the potential to enhance road safety and the reliability of automobile technology. That's all from me.